there is something deeply wrong with modern wood. In 2004, researchers at the Norwegian Institute of Wood Technology took core samples from the Urnes Stave Church, built in 1130 and never structurally restored. Under electron microscopy, they discovered something that contradicted everything modern forestry teaches. The wood fibers were packed so densely that water couldn't penetrate more than a few millimeters even after centuries of exposure. The resin channels were filled with compounds that are essentially natural biocides, and the growth rings were so tight they counted over 150 per inch in some samples. Today, you build a deck with pressure-treated lumber guaranteed to last decades, and within 5 years the wood is grey, cracked and rotting at every ground contact point. You replace fence posts that were supposed to be rot-resistant, only to find them hollow and crumbling after a single harsh winter. How is this possible? It's not because Scandinavian wood is magically superior. It's because medieval builders possessed knowledge about wood selection, preparation, and treatment that has been systematically stripped from modern construction in favour of industrial shortcuts that guarantee planned obsolescence. Before we continue, I want to hear from you. Have you dealt with rotting wood on your property? A deck that failed too soon, fence posts that gave out, or structural timber that didn't hold up? Drop a comment below and let me know what happened, because what you're about to learn will explain exactly why modern wood fails and how you can avoid it. Medieval Scandinavian timber came from trees that grew under conditions that no longer exist in commercial forestry. These were old-growth trees, often 200 to 400 years old, growing at latitudes where the growing season lasted only 10 to 14 weeks per year. The short growing season meant each annual growth ring was microscopic, creating wood so dense it barely floated. But density alone doesn't explain the durability. The harsh conditions triggered a survival response in the trees. They produced extraordinary levels of extractives, the chemical compounds trees generate to defend against insects, fungi, and decay. Resin, tannins, and phenolic compounds saturated the wood, making it naturally toxic to the organisms that cause rot. A tree that spent 300 years slowly growing in a harsh climate was essentially building its own preservative system into every cell. Modern forestry has eliminated this entirely. Commercial timber comes from plantation trees genetically selected for rapid growth, planted in rows like corn, fertilized and harvested at 20 to 40 years old. These trees grow in optimal conditions with long growing seasons, producing wide growth rings and light porous wood. Fast growth means the tree never experiences the stress that triggers extractive production. The wood is essentially juvenile tissue, low in density and almost completely lacking the natural preservatives that made medieval timber indestructible. You're not buying the same material, you're buying a product optimized for maximum yield per acre, not durability. But the degradation goes deeper than just tree age. Medieval loggers cut timber only in winter, during the dormant season when its sap flow had stopped and the tree's moisture content was at its lowest. Winter cutting had multiple benefits. Low moisture content meant less shrinkage during seasoning, and more importantly, it meant lower sugar content in the wood. Sugars are what decay fungi feed on. Wood cut in winter, when the tree has converted sugars to starches and stored them in the roots, is far less attractive to the organisms that cause rot. Modern logging operates year-round based on market demand and weather conditions suitable for equipment, not optimal wood quality. Trees are often cut during active growth periods when moisture and sugar content are at their peak, creating wood that's biologically primed for decay from the moment it's felled. After felling, medieval timber underwent a seasoning process that took years and transformed the wood at a chemical level. Logs were debarked and stacked with spacers to allow air circulation, then left to season for a minimum of 3 years, often 5 to 7 for large structural timbers. This wasn't just drying. During extended air seasoning, enzymatic processes break down residual sugars and starches, further reducing the food available to decay organisms. The wood's cell structure stabilizes, and the natural extractives concentrate and polymerize, becoming even more effective as preservatives. The timber that finally entered construction was biologically stable and chemically resistant to decay. Modern kiln drying achieves target moisture content in days or weeks by baking lumber at high temperatures. This rapid drying prevents the enzymatic and chemical transformations that occur during slow air seasoning. Worse, the high heat can actually damage the wood's structure, creating microscopic checking and case hardening where the surface dries too quickly and seals in moisture, creating conditions for internal decay. Kiln-dried lumber meets the moisture specifications for immediate construction, but it lacks the biological stability and chemical resistance that made traditionally seasoned timber durable. Once seasoned, medieval builders had another crucial advantage. They understood wood anatomy and selected timber accordingly. Every tree has two distinct types of wood. Sapwood, the outer living layer that transports water and nutrients, is light-colored, low in density, and rich in starches. Heartwood, the inner core of dead cells where the tree deposits waste products, is darker, denser, and saturated with extractives. Sapwood is biologically active and highly susceptible to decay. Heartwood is biologically inert and naturally decay-resistant. Medieval builders used only heartwood for any structural application or ground contact. Sapwood was relegated to interior use where decay wasn't a concern or simply discarded. Modern dimensional lumber makes no distinction between heartwood and sapwood. A 2x6 might be entirely sapwood, entirely heartwood, or a mix of both, and there's no grading system that differentiates. Because commercial timber comes from young trees with small diameter trunks, much of what's sold as construction lumber is predominantly sapwood. You're building with the most decay-prone part of the tree and wondering why it rots. The industry doesn't care because the wood meets structural load requirements and decay resistance isn't part of the grading standard. The treatment methods compound the problem rather than solving it. Medieval Scandinavians used pine tar, a substance produced by slow pyrolysis of pine stumps and roots in earthen kilns. The process took days and yielded a thick black liquid loaded with organic compounds that are fungicidal, insecticidal, and hydrophobic. Pine tar was applied hot, so it penetrated deep into the wood grain, filling cell cavities and creating a barrier that was both waterproof and toxic to decay organisms. Critically, pine tar is a penetrating treatment that becomes part of the wood structure, not a surface coating that can peel or wear away. Timbers treated with pine tar in the 1300s still show active preservative effects today. Modern pressure treatment injects chemical preservatives into wood under high pressure. The most common contemporary treatments use copper-based compounds that are corrosive to metal fasteners and can leach into soil. These chemicals don't integrate with the wood structure, they're foreign substances forced into the cellular matrix. Over time, they migrate, leach out, and degrade, leaving the wood unprotected. More fundamentally, chemical treatment is applied to wood that lacks inherent durability, attempting to compensate for inferior material rather than enhancing quality material the way pine tar did. There's another factor that modern construction completely ignores. The building itself was designed to protect the wood. Medieval log structures used massive roof overhangs that kept walls dry, raised foundations that prevented ground moisture from wicking into timber, and clever joint designs that shed water away from vulnerable end grain. The buildings were conceived as systems where every element protected every other element. Wood wasn't expected to survive on its own through chemical treatment, it was protected through intelligent design. Contemporary construction uses minimal overhangs to reduce material costs, places wood in direct ground contact, or uses inadequate barriers, and employs joint designs optimized for speed of assembly rather than water management. We've replaced design intelligence with chemical dependence, and when the chemicals fail, the wood fails catastrophically. Besides that, people often misunderstand the climate factor. People assume Scandinavian wood lasted because the climate is cold and dry, but that's backwards. Medieval timber survived despite brutal conditions because it was properly selected, prepared, and protected. The same wood-building traditions exist in wet climates like coastal Norway and in the continental extremes of inland Sweden, proving that the methods work across climate zones. Modern lumber fails in all climates because the material itself is inadequate and the construction methods are flawed. Here's what a 2011 study from the Swedish University of Agricultural Sciences revealed. They compared decay resistance between old-growth pine heartwood and modern plantation pine in accelerated aging tests. The old-growth heartwood showed minimal fungal colonization even after 2 years of exposure to decay-promoting conditions. The modern plantation pine, even when pressure-treated, showed significant decay within 6 months, and the treated wood actually decayed faster in some tests because the chemical treatment had damaged the wood's cell structure, creating pathways for fungal invasion. This isn't ancient mysticism, it's material science that was once common knowledge and has been abandoned because it's incompatible with industrial forestry's economic model. You can't grow 300-year-old trees on a quarterly profit schedule. You can't air season lumber for 5 years when the construction industry demands immediate delivery. You can't hand-select heartwood when the sawmill is optimized to convert entire logs into dimensional lumber regardless of wood quality. So what do you do when you need wood that will actually last? First, understand that quality timber still exists, but you have to know what to look for and be willing to pay for it. Reclaimed lumber from old buildings often came from old-growth trees and was properly seasoned over decades of use. It's expensive, but it's real wood with the characteristics that make it durable. If you're building something that needs to last, reclaimed old-growth timber is often cheaper in the long run than replacing modern lumber every decade. For new timber, seek out suppliers who can provide certified old-growth or slow-growth lumber. It exists in limited quantities from sustainable forestry operations in northern regions. Ask about growth ring density and heartwood content. A knowledgeable supplier will understand why you're asking. If they look at you blankly, find another supplier. Learn to identify heartwood versus sapwood in the lumber you buy. Heartwood is darker, often with a reddish or amber tone depending on species. Sapwood is pale and distinct. For any ground contact or exterior structural use, hand-select boards that are predominantly heartwood. Yes, this means you'll reject most of what's in the rack at the big box store. That's why it's cheap. If you're committed to a project, consider sourcing logs and having them milled to your specifications, then air season the timber yourself. This requires planning years in advance and space to stack lumber, but it gives you complete control over material quality. It's what serious timber framers and restoration specialists do when durability matters more than convenience. For treatment, seek out traditional pine tar from Scandinavian suppliers. It's still manufactured using traditional methods and is superior to any modern wood treatment for exterior applications. Application requires heating the tar and brushing it on hot so it penetrates rather than coating. It smells strongly of smoke and pine, takes several weeks to fully cure, but provides protection that lasts decades with minimal maintenance. Design your projects to protect the wood. Use generous roof overhangs, raise wooden structures above grade on masonry or metal piers, detail joints to shed water, and provide ventilation to allow wood to dry between wetting cycles. Don't rely on treatment to compensate for poor design. The wood should be protected by the structure, with treatment as a secondary defense. Understand that working with quality wood requires accepting realities that industrial construction has trained us to ignore. Real wood moves with seasonal moisture changes. Design your joints and connections to accommodate movement rather than fighting it. Real wood takes time to source and prepare. Plan your projects around material availability rather than demanding immediate delivery. Real wood costs more upfront, but lasts generations rather than years. Calculate cost per decade of service, not cost per board foot. The medieval Scandinavian peasant raising his log cabin wasn't working with magic wood. He was applying accumulated knowledge about how to select, prepare, and use timber in ways that respected the material's properties and worked with nature rather than against it. That knowledge still exists. It's preserved in surviving buildings, documented in forestry research, and maintained by craftsmen who prioritize durability over speed. Every time you choose quality material over convenient garbage, you're reconnecting with that tradition. You're refusing to accept planned obsolescence as inevitable. You're building something that will outlast you rather than something you'll replace in 5 years. If this information changes how you think about wood and construction, hit that like button and subscribe. We're uncovering the practical knowledge that modern industries have buried because it threatens their business model of endless replacement. The expertise that built structures lasting centuries wasn't primitive. It was sophisticated material science refined over generations. That science is still valid. The question is whether we're willing to apply it. Drop a comment and tell me what you're building and how you're going to apply these principles. Let's build a community that values durability over disposability and quality over convenience. The wood that will shelter your grandchildren is out there. You just have to know what to look for and be willing to do the work that medieval builders knew was non-negotiable.